Okay. Good morning, everybody. And welcome to this week's Optics and Quantum Electronics seminar. It's a real pleasure to introduce our speaker for today, Chris Anderson. Chris just a little while ago finished his PhD from the University of Chicago, where he worked with Professor David Oshlom on some really exciting spin physics technology, and he's going to tell us about that. Spin physics in silicon carbide for quantum technologies. So he did his PhD at the University of Chicago. Prior to that, he, which was actually supported, I should say, by an ND-Sec, so he's an ND-Sec recipient. Prior to that, he did his bachelor's in chemistry and physics from the University of Michigan. Yeah, lots of great stuff from the last couple of years. So I thought it'd be great to have Chris come and tell us a little bit about that. So Chris, thank you so much for taking the time.
Awesome. I hope everyone can hear me fine. Thanks for the wonderful introduction and for the invitation to speak to you all today. So as Dirk mentioned, I'm going to be focusing today on some of the work that we've been doing in David Oshlom's group at the University of Chicago in this new sort of Pritzker School for Molecular Engineering, which is a fun name, about this general idea of creating quantum technologies using spins and semiconductors. So as a brief outline, I'll first go through the materials platform that we're going to be focusing on today, which is silicon carbide with integrated spin qubits. I'll talk about the key feature that makes the system so exciting, which is its natural interface to photons. I'll talk about some of the quantum devices that we fabricated over the past few years to do sorts of new technologies. I'll sort of switch gears and talk about the control of nuclear spin quantum memories. And then I'll briefly highlight some recent work about universally protecting coherence in the solid state. So when I say this word quantum technologies, what do I mean? Well, there's sort of three major branches that one can think of, from quantum computing to quantum communications and quantum sensing. And all three of these major areas have had proof of principle, sort of groundbreaking experiments with this nitrogen vacancy center in diamond, which is a missing carbon atom next to a nitrogen substitutional impurity in this diamond lattice. That's really this prototype spin qubit that's done everything from small scale quantum error correction to nanoscale NMR to distributing entanglement over large distances. But one of the things that my group has been focused on and that my research has focused on is this idea that this diamond NV center, which is the workhorse of the field for the past 15 years, is not a unique system. There are other vacancy defects, other impurities in diamond, of which there are many experts in the audience. And there's also new defects, new spin qubits in different materials, including silicon carbide, where there's a variety of transition metal emitters, spin qubits, as well as other vacancy-related impurities, such as the divacancy center, which I'll be focusing on today, which is literally a missing carbon atom next to a missing silicon atom in this silicon carbide lattice. This defect traps some electrons. Those electrons can have both spin and orbital structure. For the spin structure, it's actually a spin equals one particle, so there's 3 levels, but we can pick out 2 of those levels as our qubit states, use microwaves to manipulate them, and they can have quite long coherence, even up to room temperature. But what makes these sorts of platforms very exciting is their ability to be able to have the spin qubit read out and initialized just using laser light. And so by monitoring the photoluminescence coming out of one of these defects, sort of with their single photon emission, we can infer the qubit state of that spin. When we cool the system down to low temperature, this optical structure resolves, making it look a lot like a trapped atom in the solid state, where we have very narrow spin selective optical transitions that we can address with resonant lasers. Obviously, for any defect, you need to be able to isolate single emitters, single qubits. And so here you can see a spatial scan of a piece of silicon carbide where there are these isolated bright dots, each of which corresponds to a single divacancy emitter in this case. So why would one think about using silicon carbide as a host to make quantum technologies, as a host for spin qubits? For one, it's available at the wafer scale. So here's a 6-inch wafer of silicon carbide and a little piece of diamond, where these two things cost about the same price. All that with silicon carbide essentially being imitation diamond. It's using imitation diamond jewelry and abrasives. It has all the same great properties of diamond. It's inert, it's chemically, it's hard, it's transparent, thermally conductive. On top of that, however, you can create a variety of nanophotonic nonlinear optical devices, mechanical devices with mature fabrication techniques with low acoustic loss. There's different polytypes with different properties that are available. All of this in a material that actually has longer coherence times than systems in diamond. In the case of the divacancy, we have this added advantage, which is essentially the emission. The single photons that get emitted by the system are in the near infrared, or sort of the near telecom, meaning they're extremely suitable for long-haul fiber optic quantum communications protocols. But the reason that silicon carbide is essentially $1 billion semiconductor electronics industry is the fact that it has use in high power, high voltage electronics, ranging from creating MOSFETs, components in electric cars, 5G technologies, to LED light bulbs, where silicon carbide was actually the basis of the first LED light bulb, or LED, in 1907. So it has a long history as well. And this advantage is something I'd like to focus on today. So we have this great system. It's sort of halfway between the quantum workhorse, which is diamond, and the classical workhorse, which is silicon. We have commercial electrical devices. We have optical readout and polarization of our qubit states. And we have long-lived spin coherence at room temperature. So we have sort of a nice blend of these two worlds. So how do we make these defect centers? How do we make these spin qubits? Well, we take a wafer of silicon carbide. You have your stackings of your silicon and carbon atoms. You can irradiate this with high energy electrons, knock out some of these atoms, creating vacancies. If you anneal the sample, those vacancies migrate, forming divacancies. And if you look at the different possible divacancies you can find in an example, this 4H polytype of silicon carbide, there's actually 4 inequivalent types of divacancies. There's 2 that I would call axial. They're sort of vertically oriented. They have C/V symmetry. They essentially look exactly like the envy center in diamond. And there's 2 sort of tilted basal divacancies that have lower symmetry. And it turns out that actually this lower symmetry can give us some nice advantages, which I'll describe later. So now I'll move on to this, this idea that these qubits are really exciting because they can couple to single photons. It's called the spin-photon interface. So it turns out that for the divacancy and for other spin systems in the solid state, certain qubit states can couple to certain orbital states, while other qubit states couple to a different set of optical, of excited state orbitals. This is another way of saying that we have spin selective optical transitions that are resolved. So if we take a narrow line laser and we scan it over a single defect, we'll see this nice optical structure with these resolved lines that correspond to single, to sort of specific qubit states, specific spin states, coupling to specific orbitals, while other spin states couple to completely different orbitals that are at a different energy. This is another way of saying that, we can use this to have spin selective absorption and emission of light. And because we have this correlation between the absorption and the emission of light with our spin state, we can create spin photon entanglement, which is the resource in the tool that we're going to use to do lots of fun science. Not only that, but we can use this narrow spin selective optical transitions to do qubit initialization and readout. So we can find spin flip transitions that have some mixing in the excited state to effectively depopulate some of our qubit levels and efficiently polarize into our spin ground state in this example. Once we're polarized in the spin ground state, we can do microwave spin control of our qubit to do arbitrary rotations. And we can also find cycling transitions, whereby we can scatter many, many photons off of this single defect that are correlated with our spin state. Then we can use this for qubit readout. And if we combine all of these things together, we can do very high contrast optically detected Rabi oscillations of the system with over 99% contrast, which means the combined errors of our initialization, our control, and our readout are all less than 1%. So we have very good control of this system as well. But single qubits, they're not really great at scaling quantum technologies. We need spins to interact. In particular, we can also think about how do we want quantum systems to interact over long distances? And we can answer both of these questions by thinking about mediating interactions through light. And that's what I'll describe here. So photons are really excellent carriers of quantum information, as many of you may know. They literally travel at the speed of light. You can confine them into optical fibers. And there's no thermal occupation for optical photons at room temperature, so they're room temperature as well. So we can have these stationary spin qubits, we can have them interface to single photons, and we can mediate the interactions through a beam splitter and some detectors. And so the way that this works is essentially through a form of Hongo-Mandel interference, where if we have indistinguishable photons coming in port A and port B, they either leave port C together or they leave port D together. In a sense, we've erased the which way information of where these photons came from. They're exiting the same port and they're identical, so we can't tell which of these two photons came from A and which of them came from B. We can use this to mediate an entanglement by putting into the ports of this beam splitter an entangled state between our spin either emitting a photon and being in one state or not emitting a photon and being in another state. And when we do this for both ports, if we measure a click at one of these two detectors, we've actually heralded ourselves into this entangled state whereby correlations exist between these two spatially separated spins, where, for example, if you measure one to be up, the other is down, or if you measure the first one to be down, the other one is up. So we've created this entanglement heralded by this click on the detector. So there's this really promising platform for doing quantum science. It's very similar to the NV Center in Diamond, where people have done long distance quantum entanglement distribution. You can think about scaling up quantum repeaters with nuclear spin quantum memories, doing all sorts of wonderful science and technology, like creating unhackable quantum communications, doing fundamental tests of physics, to really scaling up this quantum internet idea. So there's a ton of advantages. We're at solid state, we work at 4 Kelvin, we're in the near telecom, we can create nanophotonics, but it's not all sunshine and rainbows. You know, there's other issues, including photon coherence, the fact that we need to develop this system, create nuclear spin quantum memories. And this is something that I want to focus on the rest of the talk. But you know, hopefully I can sort of convince you that this divacancy system in silicon carbide has a lot of great things going for it, for building quantum technologies. So now I want to talk about some of the recent work that we've been doing about actually building these quantum devices in silicon carbide and utilizing the advantages of silicon carbide as a platform. So the first thing is essentially leveraging silicon carbide as an acoustic and a photonic material. So we can fabricate surface acoustic wave devices, basically surface strain waves, to drive and manipulate spins in silicon carbide. In this case, it's transduced by an aluminum nitride layer. You can find more details in this paper below. And you can also think about creating nanophotonic devices to enhance the optical properties of these single emitters. So in this experiment, we isolated single divacancies inside of nanophotonic cavities. We used a dopant selective etch to undercut these systems. What the real idea here is that this spin photon interface that I mentioned before, the thing that lets you do spin photon entanglement and all these nice experiments, only about 10% of the light is emitted into that zero phonon line. The rest of it is in this incoherent phonon sideband. Okay, thought there was a question.
Chris, yeah. Sorry.
Yeah.
I was just looking at Stefan's rules, so I am allowed to just ask a question. Good. Regarding the paper on the left, I thought that silicon carbide was piezoelectric, or is it? Yeah,
it is. It just we wanted it to be bigger and better. We wanted it to be stronger. Essentially.
I see.
That's the key reason. I'd be happy to talk.
Gotcha.
Talk about
Okay, that makes sense.
Why we chose that, but that's the basic reason. Silicon carbide is only weakly piezoelectric, essentially.
I see. I see. Okay, thank you.
Cool. Yeah. So for this experiment on the right with the photonic integration, basically the idea is to engineer the photonic density of states to do a Purcell enhancement, where we can increase the fraction of light that's emitted in this photon sideband in the ZPL from 10% to almost 70%. So you can make acoustic devices, you can make photonic devices, but I told you that we would sort of be focusing on this idea of using silicon carbide as an electronic device with these established wafer-scale doping and device technologies. And so the question here is, can we utilize this to make some useful quantum devices? So we call up a commercial company and we ask for what we think is a very simple electronic device, which is just a PIN diode. We fabricate devices that have electrical gates for voltage control. We have optical control through our objective. We can create single spins in this device, fabricate microwave strip lines to manipulate those spins. When we fabricate these devices, we find that indeed, you know, this is a rectifying diode, as you would expect. And we can scan over the surface of the sample and find these nice bright dots, once again, that each correspond to single divacancies inside of this electronic device. And I want to stress that these are neutral divacancies. They're a particular charge state of this divacancy. If I add or remove charges from the system, the spin structure changes, the optical structure changes, and all these nice properties go away, and it won't emit light anymore, essentially. So we have what we like to call our quantum state in our classical electronic device. We have good single photon emitters. We can cool the system down to low temperature. As I mentioned before, we have our spin selective optical transitions, once again, in the near infrared. We can use those to polarize and read out our spin states, where here you see high contrast Rabi oscillations in this device and about a millisecond long coherences, all in this commercial electrical device that we just bought from a company. So now we have spins, they're inside of this diode. What do you do? Well, you start applying voltages. So we apply reverse bias and we monitor the photoluminescence from a single defect. And at first it's happily emitting single photons. And then at around minus 75 volts, it suddenly goes dark. It stops emitting light. And the way that we can understand this essentially is that under photoexcitation, under photoillumination, our divacancy defect has a chance of photoionizing on accident. However, under zero applied field, in this case, there's sort of a bath of surrounding photoexcited free carriers that in this case is probably a little bit hole rich, such that there's always a free carrier available to sort of bring us back into the light emitting, bright, neutral state. However, when we apply an electric field, we all know that charges start to move. They start to move as a function of the electric field. And in this case, what that means is that now if we ionize our defect on accident, there's not this sort of soupy bath of free carriers around to bring us back to the neutral state. It's another way of saying that in the zero applied field regime, the Fermi level favors the neutral state, but once we apply an electric field, we have a new quasi-equilibrium that favors a different charge state of the divacancy. We can use this actually to create an electrically gated single photon source by rapidly switching across this threshold that can be as fast as megahertz, so it can be gated quite quickly. But the reason that this happens at minus 75 volts and not some other voltage is related to the fact that essentially our intrinsic region is not purely intrinsic. It's actually slightly n-type doped, such that the electric field profile in the depletion region first sort of initially only forms at this Pn minus interface, and only with increased reverse bias does it sort of move its way through the intrinsic region of our PIN diode, and at the end of the day, drop uniformly across this intrinsic region. And so what that means is, as a function of where your defect is in depth inside of this diode, you have to wait a little bit by applying more reverse bias before this field profile actually makes it to where this defect lives.
Actually, Chris,
this minus 75 volts sort of corresponds to where the defect is in depth.
Chris, let me ask you a question again. Actually, when I looked at that paper, that's something I didn't actually really understand. What is this megahertz speed limit given by first? And can you repeat why? Is it the carrier diffusion, or what sets this?
So the electrically gated speed is related to how fast you can ionize and how efficiently it recaptures its a charge. And so the ionization rate that we've seen, it's order microseconds. So megahertz is also sort of consistent. It just has to do with the laser power, essentially.
And wait, so is that this has to do with how fast you ionize, which has to do with the environment, right? Like how many charge traps do you have in the environment, or so? How fast can electrons tunnel onto or back out of the defect, right?
So the ionization is a 2-photon ionization process. So it actually very much just relates to how much laser power you crank out.
Okay, fine. So then you could pump it harder and then with the speed go up? Yeah,
so that's what we do. So this megahertz is actually only when the power is really, really high, basically at the limit of our laser.
I see. Okay.
So that's the limit, is the laser power for the photoionization.
I see. Gotcha. Okay. Gotcha. Yeah. And that's the same reason then for this creep in the intrinsic depletion region there?
This sort of growth of the electric field profile is just related to the fact that our device isn't purely intrinsic. There's actually a small amount of residual n-type impurities in this layer. And so just like in a regular PN diode, we first form our depletion region at this PN interface, but only after applying enough reverse bias that we fully depleted out that layer do we make it to the sort of more highly doped layer deeper down.
Oh, I see. Okay, so it's just a function of the voltage that you apply.
Yeah, exactly. So we're
see.
applying more and more
Not a
reverse
time.
bias,
I
and
see,
the region's
Okay.
growing. Yeah.
Okay, yeah, gotcha. Thank you.
Cool. Yeah, and this is the same physics that makes sort of regular PN diodes work. So hopefully I convince you that there's nothing fancy going on here. This is just sort of traditional semiconductor electronics.
Yeah, I had somehow mixed that in with the time scale, but those are two different things.
Yeah,
okay.
I think I kept saying time, but yeah, it's just increasing the reverse bias.
Yeah. Okay, got it. Thanks.
But if that was the only thing that I told you, which is essentially I apply voltage and I apply electric field and my defect goes away, I've killed it, it's ionized, that would be horrible. So one of the other things that we've discovered actually is that by adding a little bit of red light to our system, we can efficiently charge reset it, even under this condition where it's not really charge stable, such that even under the application of an electric field, we can get some photoluminescence from these defects. And so now we have this balance of sort of ionization rates and a reset rate from this red light, which gives us blinking dynamics of our emitter. However, we can use these blinking dynamics to uncover the photophysics of what's happening. And by varying the pump power of our infrared light and our red charge reset, we can confirm that there's a 2-photon ionization rate. It's a 2-photon process for ionization and a 1-photon process for the reset, which is another way of saying it's very efficient. And these two rates are independent. So these lasers do separate things, which means we have a deterministic way to control our charge state, either ionize it or reset it on demand. And I want to sort of stress that this photophysics is really a key thing for quantum technologies. It's related to the quantum efficiency of your emitters, how well you can initialize your qubit. And for all these nice long distance entanglement experiments, literally step one is to check and control your defects charge state. So understanding and controlling this is of vital importance. But when we think further about this idea of creating long distance entanglement with these systems, I told you that these photons need to be indistinguishable as they hit this beam splitter. The problem is different spins have different center frequencies, basically due to the strain of where they emit. The way that this has been counteracted is by applying electric fields to tune different spin centers into resonance to do this interference. So here we have this really great platform for applying large electric fields along the symmetry axis of our defect, which is actually important to reduce the amount of spin mixing in the excited state. So we once again have our narrow optical transitions. We can start applying voltages. At first, for this defect, nothing happens. And at this minus 75 volts of reverse bias, once again, the electric field starts to reach where our defect is in depth, and the lines start to shift as you expect, stark shift. Because this is a high voltage, high power electronics material, we can crank this voltage up quite high and get near terahertz level stark tuning, where here you can see different single defects that are actually at different depths in the diode, which is essentially shown by this kink behavior, where at first nothing happens, and then it starts to shift, it sees electric field, and for other defects, it takes a little bit higher voltage for it to start shifting, and some it doesn't take any voltage at all before it starts to shift. And this is once again related to essentially where these defects are in depth, and essentially watching this depletion region move through the diode. But what you also may have noticed is that these lines aren't just shifting, they're actually narrowing. And this is the really exciting part of this result, which is the fact that essentially spectral diffusion or electric noise-induced broadening on our line is a huge problem, which I'll mention later. But essentially what's happening is we have a narrow homogeneous line in the optical domain that's being jiggled around by electrical noise from free carriers. And it turns out actually just the presence or the absence of a single trap going away and coming back at a distance of 100 nanometers from our divacancy is enough to shift us by many, many line widths. But what I've also told you is that we have this depletion region that's forming where we can drift out free carriers under illumination and reverse bias. And so that's essentially what we think is happening here. Under zero applied bias, there's this whole bath of free carriers that are photoexcited that are creating a noisy environment for our spin to live, creating broadening in its optical transitions. But under reverse bias in this electric field, we've depleted out all of those free carriers, creating basically a perfectly pristine environment for our qubit to live with no electrical noise. This results in a 50x improvement in our line width, which is great. And once again, here, the takeaway is that this classical semiconductor depletion effect is the thing that's actually improving the quality of our spin-photon interface, making it narrower. And this narrowness is actually related to the optical coherence, which means that we have a more visible interference dip when we start to interfere these photons on a beam splitter, which means that our entanglement fidelities and entanglement rates for long distance interference become much higher. And it's actually squared. So a 50x improvement in your line width is actually like a 2500 times improvement in the entanglement rates, which is quite good.
So, Chris, I have a question on this and the sort of the mechanism that's happening here, and how, because I guess a couple things are happening. One, you're depleting free carriers, and you have this depletion region, and second, you're applying a Stark shift, so you have a field. And how do you discriminate between those two effects and say which one is the most relevant?
So this was something that we obviously wanted to figure out. As far as we could tell, the only mechanism to narrow the lines while applying fields were related to how much asymmetry you're adding into the orbitals. So, you know, for these divacancy centers, they have sort of two branches with applied strain and electric fields, you know, along the axis, they shift together. I don't know if you can see my hands, but with transverse fields, they sort of shift apart. And maybe as you're breaking the symmetry of that system, you're changing its susceptibility to noise. So one of the things that we tested essentially is that this transverse asymmetry, basically what the excited state orbitals look like, had a very different structure where essentially the asymmetry kept going up, but the line width kept going down. So at least as far as we could tell, there wasn't an easy way for us to connect the electric fields effect on where the orbitals were and the line width narrowing, as far as we could tell. But I'd be curious to hear your thoughts on that later.
Okay, interesting. Thanks.
Yeah, so we have a system that's stable for many hours. We see 20 megahertz lines. It's basically only limited by the temperature and the instrumentation at the time. We can actually go back and do better measurements, and we actually do see lifetime limited lines in the system, which is really great. We can flip this problem on its head and sense single electrons. You can think about sensing single electrons. We can think about mapping both fields, which is line position, and charge density, which is line width, in these commercial semiconductor devices, which is sort of a fun thing to think about. Where the real takeaway here, once again, is we have long coherence times, we have tuning, we have spin control, we have very narrow line widths, and charge stability that we all got by simply putting these defect centers that we know and love inside of commercial electronic devices. Not only that, you know, because we have this wide tuning range and we have very narrow spectral lines, we can think about spectrally multiplexing entanglement channels over telecom fiber with maybe over 40,000 channels. That's the ratio of the line width to the tuning range. On top of that, there's all sorts of new opportunities that one can think of for electrically controlling the spin states, electrically reading out the spin states, using the charge states of these centers for sensing, doing AC modulation to do flow K engineering of the orbital excited states, maybe reducing electrical noise for quantum sensing improvements. Where one of the fun examples I'd like to show you about today is this idea that for certain divacancies that are limited by electrical noise, we can apply voltages, use this depletion effect to clean up the free carriers, and actually see some increase in the coherence time in this system. So there's lots of great opportunities for increasing coherences and also new sorts of quantum devices. So I hope I've convinced you that we've been able to combine this billion-dollar industry with these controllable quantum states, that we have this way to engineer the electrical environment, the electrical noise of our qubit, that we have this very good tunable single photon source, the importance of this charge state control and understanding the photophysics of what's going on in your system, and these opportunities for linking spin and charge in the future. So now I'd like to switch gears and talk a little bit more about creating nuclear spin quantum memories. So these electronic devices sort of provide this ideal spin photon interface. But the other key ingredient you need is the ability to have nuclear spin quantum memories as sort of local multi-qubit nodes. That's the sort of other half of the story. It's also important for all sorts of applications for sensing, computing, and communications. This understanding and control of the nuclear environment is key. Now, these nuclear spins, they're amazing. They have about 1,000 times smaller magnetic moment than the electron. This means they can have days-long T1 times and very, very long coherence times of minutes to hours maybe. Really, nuclear spins are one of the best quantum objects that we really know of. And they're really a key in creating quantum networks and distributing quantum entanglement, where you can have sort of your electron spin talking to light and also talking to a bunch of nuclear spin quantum registers to sort of scale your system. But nuclear spins are what I like to call a double-edged sword. They're randomly placed they're uncontrolled, and each of those spins is a little tiny magnetic moment. Each of those nuclear spins, the spinful isotopes of the host crystal, they carry a magnetic moment, and we know that our qubit levels are sensitive to magnetic fields from the Zeeman effect. And so each of those little magnets in the environment create a fluctuating magnetic noise that our defect feels that reduces the coherence of our qubit states. And this is exactly the limit of this 1 millisecond. So we know exactly what's limiting us. It's the nuclear spins in the environment. So how do we overcome this? How do we talk to nuclear spins? How do we deal with this noise? Basically, we think about this by coupling them because they have different spatial locations. They have different hyperfine interactions with our central electron spin. And so through difference in the hyperfine strength A, we can actually start to address different nuclear spins in the lattice. And for certain nuclear spins that are very close to our central electron spin, the hyperfine coupling is strong enough such that we can actually resolve the nuclear spin state induced splitting in our electron spin transition frequencies. We call these strongly coupled nuclear spins. Because those transitions are resolved, we can use them to create controlled rotations. And as all of you know, controlled rotations are the basis of creating entanglement. So we can actually go through and create an entanglement between a single divacancy spin and a single nuclear spin in silicon carbide. But the flip side of this actually is that these strongly coupled nuclear spins are actually not the ones that you really want to use for a lot of applications. And that's because your mechanism to control those nuclear spins, the hyperfine interaction, is also the mechanism by which your nuclear memory becomes disturbed by what you do on the central electron. So you want this memory to be robust. You want to be able to do lots of operations on your central electron. So you actually want low hyperfine coupling. You want something that's very robust. It's only weakly coupled to your electron spin. On top of that, the number of literal lattice sites that can create a strongly coupled nuclear spin register, there's only a few. So scaling up to, let's say, 10 nuclear spin qubits is not reasonable using this strongly coupled spin register that I told you about before. So how do we talk to these weakly coupled spins? Well, we borrow techniques from AC sensing, where you can have a Hahn echo. You might cancel DC magnetic fields, but if you have an AC field, for example, from a nuclear spin, you can constructively add the phases instead of destructively interfering those two phases. And so if you add a bunch of pi pulses, you can actually create a very narrow filter function that only selectively adds the phases from a particular frequency of magnetic field noise and cancels all other sources of noise. And in this case, if you tune up the pulse separation to sort of the Larmor frequency of a nuclear spin, you can selectively talk to just that one weakly coupled nuclear spin. So we can do this experiment. We can change this tau in both natural silicon carbide that has lots of nuclear spins in the environment and isotopically purified silicon carbide that we grew and isolated single divacancies inside of. And so in a sense, each of these spectra, which is changing tau, is a probe of the surrounding nuclear environment of this single electron spin. And you can see for the natural silicon carbide, it's sort of a mess. There's a bunch of features, there's a bunch of peaks, and it's really hard to identify the signature of a single nuclear spin. Meanwhile, in the isotopically purified sample, we see these nice isolated dips corresponding to interactions with just single nuclei. We can use this and vary the number of pulses or vary the interaction time between our electron and our nuclear spin to create a controlled rotation, which is the basic 2-qubit gate for creating entanglement with these systems as well. But there's a very interesting question here. Obviously, if I have too many nuclear spins, it gets really crowded and it's hard to see. That's what I sort of showed you up here. It becomes hard to address nuclear spins. But if I have too few nuclei, then there's no quantum memories to play with. And so we actually talked to our theory friends and we came up with a model to explore this trade-off. And it turns out that there is basically a right answer, which in this case is around 0.5% or a few tenths of a percent, where you've maximized the number of quantum memories that you can control in this way. On top of this, the type of nuclear spins that you can talk to in terms of their hyperfine interaction also changes as a function of the isotopic concentration. So as you purify more and more and more, you can address these more weakly coupled nuclear spins, which are the ones that you want to use for quantum networks, for example.
Chris, can I ask a question?
Yeah, go for it.
The model to which you just referred, does that appear somewhere?
Yeah, that's in the methods of this Nature Materials paper and the supplement.
Okay.
If you have any questions about it, we can catch up later too. But hopefully you should be able to find it in that paper.
Thank you.
And Chris, maybe a related question. So looking at the x-axis of those plots, how long are the operations necessary for interacting with the nuclear qubits, and how does that compare to the lifetime of the electronic qubit?
Yeah, excellent question. So obviously, like when you have something that's more weakly interacting, the trade-off is you're weakly interacting with it. It's only coupling very weakly, so the gate times become quite long. So here, I think the longest gate time we considered was 1 millisecond, I think. We have some assumptions about what parameters we thought were reasonable versus not reasonable. For this system, at these temperatures, the T1 time is essentially seconds or longer. So, and you're doing all these pulses. So, you know, we've seen, you know, many milliseconds of coherence. So we're well within that regime in this case.
Sorry, the coherence of the nuclear spin or of the electronic spin?
Of
And
the
when we're
electron
talking about the
spin,
coherence of the electronic spin, is there something special we need to do to control the coherence, the natural intrinsic coherence versus various decoupling techniques?
So the question is, what do we have to think about for the coherence of the electron spin in terms of purifying?
Yes.
Yeah, so there's obviously a sort of second thing that happens when you reduce the isotopic abundance of the nuclear spins in the environment, which is your lines become narrower, the coherence times naturally get longer. This is all wrapped up in this model we made, which is essentially using cluster correlation expansion techniques to high order. So we actually model different nuclear environments at random and take averages over many instances of different possible nuclear configurations. So what's happening under the hood, maybe we can discuss later, but the coherences and the T1 times for the system are very long. And the effect of the isotopic concentration on our line widths and what that means for this control protocol is already taken into account in this model.
Okay, thank you.
Cool, yeah, great questions. But yeah, the moral of the story here is when you're designing these spin-based systems, you need to think about engineering your nuclear spin environment to make ideal and to maximize the number of nuclear spins that you want to use. So, you know, we had a nice feature on this, which is the key takeaway, which is we have these nuclear spin memories as the key resource in our sort of future telecom quantum networks using divacancies in silicon carbide. There's some other things in this paper that are nice to highlight. You know, we have very high gate fidelities. We can do coherence extension using CPMG. As was mentioned, when you reduce the nuclear spin environment, you also get long coherence times. They're not as long as you might expect, and the limitations of that coherence is actually due to not the nuclear spins anymore, but the paramagnetic electron spins that start to limit you at that level. So the sort of takeaways is, you know, we get these record coherence times from the isotopic purification. We get sort of state-of-the-art electron spin control fidelities. We isolated, controlled, and entangled single nuclear spins. And we came up with this model for maximizing the number of nuclear spin quantum memories that one might use. And if you remember, there's these sort of strongly coupled nuclear spins that have high hyperfine coupling. And we have weakly coupled nuclear spins, of which there might be many in the lattice that we can address. And so the sort of hierarchy of memory is very similar to classical computing, where we have sort of our logical electron spin that can talk to light. We have, you know, fast operations on a few qubits of the strongly coupled nuclear spins. And then we have our long-term robust memory storage in these weakly coupled spins. So at the end, I sort of want to also briefly highlight some of our other recent work about protecting coherences even longer. So besides isotopic purification, reducing the magnetic noise, what else can you do? And so one of the interesting questions that the field has been talking about a lot is this idea of symmetry. So the divacancy in silicon carbide and the NV center in diamond, they have this C3V symmetry. And one of the things that the field has really been going to is to high symmetry defects, such as the group 4s in diamond, that once again, many of the people in the audience are probably experts on. And the real key feature of this system is it has inversion symmetry because of this higher symmetry. And that means it has a vanishing electric dipole moment. And so all of this work I told you about you know, engineering the electric field noise environment, this depletion, it makes the divacancies have nice lifetime limited lines. But you can also approach this problem by making your defect less sensitive to that noise. And that's the strategy for these high symmetry defects. So there's a natural question of like, okay, well, we went to higher symmetry and things got better. What happens when we go to low symmetry? And as I mentioned in the beginning, there's this other class of divacancies, these tilted basal divacancies that actually have slightly reduced symmetry. So does that hurt us? Does that help us? Are there new opportunities? Are there less opportunities? Hopefully I can convince you that there's actually some really interesting things you can do with lower symmetry as well. And one of the key features actually is that because of this reduced symmetry, there's actually a transverse zero field splitting for this spin 1 particle that mixes the +1 state and the -1 state at zero field, creating these new eigenstates and this splitting 2e. And the other part of this is if you apply z-axis magnetic fields, you'll notice that there's actually a first order insensitivity to magnetic noise due to this mixing. It's another way of saying that we have a clock transition, something that's insensitive to our noise at zero field. And so at this zero field point, we actually can get extended coherences in a naturally abundant crystal, where usually we would measure something like 1 or 2 microseconds, and here we can get 70 to 100 microseconds. But the sort of key question is, can we make this better? Can we engineer this to be a little bit more protected? So we have this transverse zero field splitting, as I mentioned, and we can combine this with sort of continuous dynamical decoupling or continuous driving of qubit states to make some interesting new physics happen. So if we drive between these minus and plus states, we can dress them, create an Altler-Towns splitting of these levels, creating this whole new, nice set of forest of levels. And we can isolate a few of them through spectroscopy using this third level, which is our MS equals 0 level, drive transitions between all of these different levels, our 0 state and these 2 dress levels. And we can also drive transitions between these 2 new dress states. And that's done electrically between these 2 new qubit states. So we designed a device that had both magnetic and electrical control, and we can redefine some new qubit states in this new dressed Hamiltonian. So why would we do that? So in the undriven case, we have this first order insensitivity to magnetic noise, giving us a clock transition and some nice protection. But we actually have first order sensitivity to electrical noise, which is not great actually in these systems. As I was telling you, electrical noise can be an issue. But when you drive the system, you actually can get quartic suppression of magnetic noise by the addition of this continuous dynamical decoupling drive, essentially. On top of that, you also get a clock transition in terms of the electrical noise. So you've essentially opened this gap for both the magnetic noise, which is now suppressed to second order, and you've created first order suppression of the electrical noise. So there was a nice feature on this that essentially goes to this idea that you've multiplied the effect of your continuous dynamical decoupling driving and your clock transition to get, quartic suppression of the magnetic noise. And so the system at the end of the day becomes insensitive to electric fields and strain and magnetic fields to second order. And you can also think about finding the same sort of Hamiltonian and designing this same system in other quantum platforms like superconducting qubits. Sometimes we'll hear people talk about these like dynamical sweet spots. So does this work? So we can do a Ramsey experiment in this driven basis. We measure a T2 start time that's over 20 milliseconds, which is one of the longest reported ever electron spin dephasing times. It's much better than if we hadn't done this technique. And it's also compatible with Hahn echo. So we can put in a pi pulse and measure 64 millisecond long coherences, which is even better than our isotopically purified substrates. So this is really a great way to protect the coherence in your system. So as a whole, I hope I've convinced you that we have this really exciting platform for doing wafer-scale quantum science. We can create mechanical devices to manipulate our spins, optical devices to enhance their properties. We can create electrical devices that give us new opportunities. We can isolate and control nuclear spin memories and extend our coherence times of our spin qubits. All of which combined gives us this really exciting platform for doing scalable quantum communication nodes. Once again, with this idea of having narrow spin photon interfaces, nuclear spin memories with long coherences, along with new opportunities for creating quantum electronic devices using silicon carbide. So with that, I'd like to thank you all for your attention. Our funding agents, our collaborators in Sweden and Japan, David Oshalom, my PI, and Alex Barassa, who's been a sort of assigned projects. And with that, I'd be happy to take any more questions.
Awesome. Thanks so much, Chris. Very nice work. Questions? Let me start it off then. Regarding the fabrication of thin membranes that you would want for photonics, for example, you've shown one method of this photoelectrochemical etching.
Mm-hmm.
Does that actually extend to large membranes that are sort of wafer scale?
That's a good question. So one of the problems with that technique that maybe is not so obvious is that the undercut rate or the etch rate is very, very slow. And so it's sort of easy to undercut nanobeams and maybe small suspended structures, but doing anything sort of wafer scale where you really need nice undercuts, it's maybe not so good. However, we're not an electrochemistry group, so maybe like you can figure it out. But we haven't taken the time to do that.
Yeah. So you think that it would be difficult even if you did have sort of etch pits defined throughout the wafer? I mean,
I wouldn't go and tell anyone that it was impossible.
Yeah.
I think like if you do it, like you can probably figure it out. I don't think it's like a dead end.
Yeah.
But I also do think that there's obviously some really exciting other platforms of way to get thin film silicon carbide.
Yeah.
People can create silicon carbide on an insulator, obviously. So there's
that's
multiple ways you can think
cut,
about
right?
it.
And that's a smart cut or crystal ion slicing method.
So the silicon carbide on an insulator is not smart cut. It's actually just like a wafer bonding and then a polishing. So they don't actually do the ion slicing.
The backside, I see. Okay.
Yeah, and so people are thinking about combining these two methods as well to get some advantages. So
Gotcha.
also, 3C silicon carbide, which is one of the other polytypes, you can grow thin films on silicon, which is easily undercut. So there's some opportunities there as well.
But the emitters in that are not as good, it seems.
Well, I think we have a divacancy in 3C silicon carbide that we know really well, and it works really well. The problem is not that the emitters don't work, it's that the materials are less high quality than potentially the homoepitaxy on silicon carbide. So all of our materials are silicon carbide substrate, high quality epitaxy on top. When you grow 3C on silicon, there's a lattice mismatch. It's just sort of a mess. Also, they don't have as good control of the doping, so the charge stability can become an issue. It just, we haven't quite figured it out, but it's not impossible.
Gotcha. Thank you. Okay. Other questions?
So great talk, Chris. Thanks. When I think of these decoherence protected subspaces that are produced by continuous drive, it's sort of like there's a series of decoupling techniques that's continuous dynamical decoupling. And one disadvantage is you're sensitive to like the Rabi frequency of your drive field or amplitude noise. So how do you get around that in this experiment?
So yeah, that's the trade-off that maybe I didn't say. It's so there's always trade-offs in science, right? So we've traded off magnetic sensitivity and electrical sensitivity to our drive strength, our Rabi power. And in the science paper, we actually developed a technique to sort of stabilize our sensitivity to the power fluctuations in our SIGGEN. Because those are actually quite slow, and so it's easy to feedback on those essentially. Also, at that point, it sort of becomes like an electronics problem and not like our qubit has a noisy environment that we can't control. It's something that you can control. And at the end of the day, yes, there's a trade-off, but we got this massive boost. So like, it seems like the trade-off was worth it in a sense.
Yeah, definitely. It looks great. So thanks for that.
Yeah, it's definitely something that you have to think about. There's also, you need to drive it sort of hard. And so maybe there's like a power dissipation thing, and your qubit frequency becomes the drive strength. So maybe it's a low frequency qubit, which might have some other issues. So there's definitely trade-offs, but
so to continue on that point of this, what is this qubit and what is the state that you're getting? Is it possible to map that into photonics in a spin photon interface way, this decoherence protected qubit?
So the nice thing is this decoherence protected qubit, it's it's nothing weird. It's nothing special. It just, you know, when I say that, I mean to say that when you go to do readout, you can just turn the drive off and do your readout, and everything works the same. So when we read out the state, all we do is we turn the dressing drive off and we measure the population in the MS=0 state. And that MS=0 state is not sort of affected by the driving. We just sort of use it as our sort of auxiliary state to sort of probe what's happening. And so you can map all of the dynamics in this new subspace into sort of your regular measurement basis. So there's no real downside for that, I would say, as long as you're willing to do some extra pulses. I think it should work the same.
Thanks.
But yeah, that's an interesting question. We've definitely thought about that a little bit.
Okay, any other questions?
I have a practical question. Thanks, Chris, for the nice talk. How bright are these emitters usually, and do you fight against total internal reflection in some way? I saw that in your PIN diode work, you did.
Yeah. So
yeah,
great question. I mean, you know, there's always this question of how do these systems benchmark, and like, what's the count rate? What's the quantum efficiency? Usually I would say our count rates without a solid immersion lens, which is sort of our benchmark, 0.85 NA microscope objective, we would get like 50,000 counts per second. However, this is something obviously that's vitally important to doing basically any future experiment. And so we've both done solid immersion lenses and also done higher NA optics and improved all of our measurement techniques. So now we're pushing more like, you know, 500,000 kilocounts to maybe a mega count, which is comparable to the NV Center and Diamond, I would say.
I see. And that's all in bulk, right?
Yeah, so I would say we get, yeah, so in bulk, in the experiments that you just saw, they were all 50,000 counts per second.
Yeah.
New experiments were maybe pushing 150 in bulk, 150,000 counts. And with a solid immersion lens, we're getting a factor of 5 improvement or something like that. And so we're approaching hundreds of kilocounts to maybe a mega count per second with a solid immersion lens.
So since you have these photonic crystals, didn't you like fabricate scatter structures like, you know, like pillars and things like that, so that you get
yeah,
higher
so for
upward?
that photonic crystal experiment, we actually just measured it directly with our microscope objective because the coupling wasn't so high that it was super confined to the waveguide. It sort of was leaky vertically. And for that, I think we saw like 200,000 counts per second, which is not really related to like how much the lifetime's changing. It's really just the collection efficiency. And we've also made, you know, micro pillars and things like that that also show enhancements, but probably everything's in around the 100,000, like 100 kilocount range.
And sorry, just to be clear, are those numbers into the zero photon line, or is that combined zero photon line plus photon sideband?
So that's just the photon sideband at this point. We're currently working on sort of isolating out the zero photon line. So for the photonic measurement, that was all sideband. So actually, like in a sense, it's bad because the photon sideband we were filtering and it had 70% of the lights. So maybe there's some modifications of that number that could be made, but most of the numbers I've been quoting you is just the photon sideband.
Gotcha, thanks.
All right, thanks.
But yeah, this is something that we're working on getting those count rates up as best as we can. And this is obviously an opportunity for where photonics can really help out as well.
Yeah. Okay, so we're at about the hour. So many thanks again, Chris. So with this, we're gonna move on to the next part. Which is the direct. So if you signed up to meet with Chris, you would have been provided a link. So we'll resume with that. Awesome.
Okay.
Thank you
Yeah,
again.
thanks.